Welcome back. In this session, we'll learn how to design different FIR filters in Matlab. Let's start. Let's open Matlab. Now let's open FDA tool that's available in Matlab. So we can see a window pops up that looks like this. All right. So our goal is to design FIR filters. All right. So first, let's see the low pass FIR filter, but that we are going to follow windowing technique. Means the technique that we'll learn is known as windowing technique. And then what we'll do, we'll specify the order of this filter. Suppose order of the filter is 2. Then we'll use the window, which window we want to use. For example, there are different type of windows available here. First, let's see the rectangular window. Now you can see the frequency response of this window as well. Means you can see the time as well as the frequency response of this rectangular window. Let me show you that. You can have a look. I hope you are able to visualize this. This is the frequency response of this rectangular window, and the size of this window is 2. You can check the size of the window is 2 because we are keeping only 2 coefficients of this window, and this is the frequency response of this window. All right. So let me switch back to the FDA tool. All right. So let's design the filter, and let's use again the normalized frequency. So we say the cutoff frequency, suppose is at 0.5. All right. So then I hit the design filter. Then this shows me the cutoff frequency is 0.2, and I can check the different characteristics of this. So this is the magnitude response of this filter, whose magnitude response of the filter of size 2 means we have only 2 coefficients of this. And I can check the phase response of this. You can see the phase is varying linearly with frequency. It is decreasing linearly with frequency and then again decreasing from 0.8. So you can say this is a linear phase filter, as the most important advantage of FIR filters is these are linear phase. All right. So you can say group delay will be constant, phase delay will be constant for this filter. This is the impulse response. You can see there are only 2 values of this impulse response, 0 and 1. All right. Then what we do, this is the step response of this filter, and this will give you the coefficients of this filter. All right. So these are the coefficients of this filter. All right. So let me show you a filter of order 10 now that we design using this rectangular window. Let me show you first the window. This is the window. You can, as you can see, there are now the size of this window is now 10. You can check it. Sorry, this is not that window. Where is that window? This is the window. This is that window. All right. So this is that rectangular window of size 10. All right. Means we'll use this window to truncate our desired frequency response. All right. So let me switch back to FDA tool. So this is our FDA tool. Now we want the cutoff frequency to be this time equal to 0.7. Sorry, 0.7. And when we hit the design filter, this will design the filter, and let me show you the magnitude response. So this is the magnitude response of this filter. All right, so this is the magnitude response of this filter whose cutoff frequency is 0.7. Again, you can check, yes, indeed 0.7 is the cutoff frequency. Means the this gain of this filter should be equal to 3 at 0.7. That you can check from here. All right. So now you can check the phase response of this. Again, it is varying linearly. You can check group delay will be constant, phase delay will be constant. This is the impulse response of this. As you can see, there are 10 samples of this. When 10 samples of this filter. All right, because we kept the window size to be equal to 10. And then you can see the step response will again contain 10 samples that you can check. So this is the step response of this filter. Then you can see the pole 0 location. You can see there are 10 zeros. There is no pole. Actually, there are zeros. There are poles at the origin, but these do not matter. That's why this filter is inherently stable filter, because all the poles all the this poles are located at the origin. There will be 10 poles, there will be 10 zeros also, but these poles, the poles at origin do not matter because these are at the origin, means they are contained inside the unit circle. All right, so this is how we design a filter of size 10 by using rectangle window. Now if we use a different window, let me show you a Han window. Let's suppose we use a Han window or Hanning window. So let me first show you the how does this window look like. So this is the uh, time domain description of this filter, and this is the frequency domain description of this window. Sorry, horn window. This is the window that we are using to get truncate our filter. All right. So let me go back, and this is the FDA tool. Then let me say the cutoff frequency is at 0.3, and I hit the design field. And let me show you the magnitude response. This is the magnitude response. Now the cutoff frequency is at 0.3. You can check the cutoff frequency is at 0.3. You can check it. All right. So I hope you have got the idea. You can change the order to say, suppose 50. Now hit design filter. You can see this filter has order 50. All right. And you can see the cutoff frequency is now more sharp. This has more sharper transition characteristics. All right, now you can also check the phase. Phase is again varying linearly. This is the impulse response of this filter, and this is the step response of this filter. So this is the impulse response of this filter, and this is the step response. All right, so this is using Han window. Now let me show you one Hamming window. Let us see the Hamming window of size, suppose 12. So let me first show you the window, Hamming window, and I assume this one is the Hamming window. This is the Hamming window that we are going to use to model our, truncate our the desired impulse response. And let me switch back to this and design this filter. And let's suppose the cutoff frequency is now 0.4. This is normalized cutoff frequency. This is the step response, and this will have 12 samples. This is the impulse response of that filter. And let me show you the magnitude response. This is the magnitude response of that filter. And this is phase delay. This is group delay of the filter. You can see all these filters have this constant group delay and phase delay. Why? Because this involves linear phase. That's why the phase delay and this group delay will be constant. All right, let me show you one more window that's referred as Bartlett window. Let's see the Bartlett window. Let me first show you the window. This is the Bartlett window. This is the Bartlett window, and this is the time domain version of this, and this is the frequency domain response of the same window. All right, so let me switch back to FDA tool, show you the filter, design this filter, and let me show you the magnitude response. This is the magnitude response of this, and this is the magnitude as well as phase response, right? This is the impulse response of this filter. This is the step response of this filter. This is the location of poles and zeros, right? All right, please play with these different type of windows. Now let me show you last one is a 2K window. So alpha is, there is one parameter that's referred as alpha, and this is the 2K window. This is 2K. This is the time domain description of that window. This is the frequency domain description of that window. And finally, let me show you the filter. This is the filter, and let me show you the magnitude response. This is the filter that we designed using the 2K window. 2K. Okay, 2K is the name of the mathematician, and this is the filter that we designed, FIR filter that we designed using this. And all these filters are low pass filter. Now you can design a high pass filter also. Let me suppose you are designing this filter using a rectangular window, and let's suppose you are using again the normalized frequency, and the cutoff frequency of this will be at 0.4. So we'll design this filter. This you can check is now a high pass filter, and this is the correct. Now if I change the order to 50, let me change the order to 50. So you can see now this has sharper transition characteristics, right? So this is a high pass filter. FIR filter designed using windowing technique. So we are using a windowing technique. There are other techniques that you can use to design an FIR filter. For example, the least square is very popular these days. So you can design it using a least square, right? Let me show you the normalized frequency. So W stop is at suppose 0.5, W pass is at 0.3. So this is the filter. Sorry, F frequency must not be non-decay. Yes, it should be greater than this. It should be W pass should be, because we are designing a high pass. Let me show you low pass. Let's go to low pass. W pass is 0.3, W stop is 0.5. So let me design the filter. This is the filter design using least squares approach. We haven't discussed this, but there are several approaches to design an FIR filter. We discussed only windowing technique, the filter designing a FIR filter using windowing technique. And there are several windows available in this that you can use to design a FIR filter. All right. So please play with these different windows and see what happens to the magnitude response and phase response, what happens to the group delay and phase delay, and how the impulse response and step response of this filter changes. All right, let me end this session here.